So what we're going to be looking at here, assuming I can get my mouse to work, yep, there it goes, sorry, is our ether synthesis. So in ether, if we remember correctly, perhaps from diethyl ether from the lab, take a look at our little flying bat, and we have what is known as diethyl ether. So each of the branches is 2 carbons, so we could call it diethyl, and then we just drop in the functional group, ether. There's really kind of 2 approaches to making an ether. We can make a leaving group and make that leaving group good, or we can go through and we can make a good nucleophile. The good nucleophile is named after the particular synthesis, so Williamson synthesis. So we have seen at least the first one make a good leaving group, okay? And we saw that when we added dilute H2SO4. Okay, and what would that dilute, so try and figure out what I'm trying to write here, dilute do? Well, under dilute conditions, we do have that strong acid present, which is really just saying we have H plus floating around. So we can take the electrons from our nucleophilic oxygen, shuttle across over to there, and we would then have kind of the rest of our structure with the hydrogen connected. We now have this good leaving group. That leaving group could theoretically, and this is going to be mechanistic dependent or structure dependent, but it's probably going to be forced off to leave on its own. We would form a carbocation, and it would say, well, what could we do? Because we were running under dilute conditions, we still have starting alcohol floating around. That alcohol can now come in, and react. We'd have our oxygen, there's the H still remaining. We'd then be connected to that new structure. That oxygen would be positively charged because it just lost a pair of electrons or shared a pair of electrons. A base could come through in solution, remove that hydrogen, and we would end with our ether. So this does get us ethers, but it does bring up a couple big issues. First and foremost, sterics. This is going to be a very sterically hindered structure, particularly if we run it in this type of mechanism with the formation of a carbocation. If we remove some of those carbons, that could work to limit some of this. But again, we're going to slow the rate of the reaction because of it being a protic solvent. It's going to want to follow an SN1 reaction, okay, or an SN1 type as opposed to the SN2 type. So it would slow kind of the rate of the process of our ether. The other problem with this is that this guarantees a symmetric ether. The carbon pieces on either end have to be the same because we're going through a dilute acid environment. We wouldn't be able to mix in some of one alcohol and some of another, or if we did, we'd get a giant mess of different products coming out of it, of different ethers. So we really only end with symmetric ethers. We're going to be a little limited in the chemistries associated with those or the symmetries associated with them. And so it's not the greatest synthesis, okay? It would work, but again, not the greatest synthesis. So what we would want is something to be a little bit better. So instead of trying to really activate our electrophile by making that good a leaving group, what we're going to do is flip this and try and throw in a really good nucleophile. So if we're going to throw in that nucleophile, and if we just run this, say, an example with what we've got above, that nucleophile would need to be negatively charged so that it could come in and attack our carbon. We're going to notice some issues kind of right away with this. So first and foremost, that negative charge is going to react with the most positive thing present. That carbon is positive, but so is our hydrogen. So this potential nucleophile is going to become problematic because it can attack either of those 2 positions. Another thing to consider, I need to end with an ether. Okay? In that ether, I have to have that oxygen in there. If we look at how our nucleophile is going to react, what it's going to do is kick this piece out as a leaving group. Okay? That's a bit of a problem. okay, for a couple reasons. Number one, it doesn't bring in the oxygen, which means this nucleophile has to have oxygen and then something else out here. Okay, so we've identified something about those pieces. The other thing is that if we ejected that, we would have OH minus, and that's a bad leaving group. So when looking at the problems with this synthesis, what we're trying to do is address ways that we can alleviate some of these issues. So to start with, we're really making a good nucleophile, okay? And so that's absolutely true. We're going to end up using some kind of negative OR, right? So we could start with, say, an alcohol. Let's just pick ethanol. And if I want to make that a good nucleophile or a better nucleophile, I need to remove this hydrogen so that I can form that negative charge on the oxygen. How do I go through and convert that to a negative oxygen? What would I need to add? I'd need to add a strong base. The base electrons would come through, pick those up, and shuttle those across. We need to ensure that this is as strong a base as possible so that it really removes the hydrogen. And additionally, it ensures that all of that starting alcohol converts across to our good nucleophile, right? So that we don't get any kind of secondary weird reactions with unreacted alcohol reacting with this good nucleophile. So now we have to address the other half of this. The other half was that was a bad leaving group. So I now need to react this with my electrophilic species, okay? That electrophilic species, if it was another alcohol, causes a problem because now our good nucleophile could attack here or it could attack here. Right? In one case, it acts as a nucleophile. In the other case, it acts as a base. So that OH is not a great structure to have on there, a good piece to have in our electrophile. I want to make sure that that OH chemistry or that acid chemistry isn't there. So I want my leaving group to not be an OH. I want that leaving group to be something else. I want it to have very limited chemistry. A halide works out really well. So now what can happen is our nucleophile can come in, backside attack, kick out bromine as a leaving group, and what we would have would be our original starting piece that would then connect. And of course, I probably should have picked something like propyl, would connect to that one new carbon in this case, and I had a Br minus. I've now gone through and generated and formed an ether, but at the same time, I've increased yields, and I've made sure that that ether is not symmetric, or is an asymmetric ether. Okay, because we had to nuance some of the challenges behind that chemistry, this is why Williamson got to attach his name to it, right? Because it was a challenging reaction to set up, and we had to make some significant changes to our reagents to force that to occur. So Williamson gets to attach his name, okay? So in that process, we started that off with a strong base to activate our alcohol, okay? To really take that alcohol that had all of those chemistries. Okay, what were those chemistries again? We had the oxygen as a potential nucleophile and base. We had the hydrogen as a potential acid, and we had the carbon as a potential electrophile. All of those chemistries make this challenging. So what we went through and did was throw in a strong base. Because it's now a strong base, that forces the acid-base chemistry. Okay? So our reagent choice changes or dictates how the alcohol is going to respond. Once we've removed that chemistry, the new structure that comes out of that negatively charged oxygen, now dictates how the next reaction runs, because now we don't have the acid, we don't have the electrophile, all we have is that nucleophile or base. Okay? So if we want to limit the base characteristics of it, we would choose an alkyl halide that would support an SN2 mechanism. So if we look at the drawing shown below, right, or shown there, would we expect that alkyl halide to be a good choice for the Williamson ether? If we assume everything on there is standard, so we're calling these carbons, CH3, CH3, CH3. Should that work well in the Williamson ether? Probably not. Why? That's a sterically hindered structure, and what we're talking about is this strong nucleophilic attack, backside attack, SN2, to force this reaction to happen. Sterically hindered, it's going to limit that reaction. So what we probably want is something that's a little bit less sterically hindered for an alkyl halide. Right? So we're trying to evaluate the structure and pieces of each of those reagents as we kind of advance our way through. And it's addressing really those differences that's critical to looking at these reactions. So we've got an example reaction shown above. In this case, a symmetric one, pretty much what we just walked through. Okay, KOH is our strong base. Okay, the potassium makes it a slightly stronger base than if we used sodium. And we've got our ether. Okay, so this is a good opportunity to take advantage of what we looked at in a video 3 or 4 videos ago for synthesis. Okay, we want to consider how can we use Williamson ether synthesis to make either of these two structures. Okay, so MTBE is on the left. That would be methyl tert-butyl ether, and then anisole on the right. So we want to come up with a synthesis that would allow us to do this. Right? In that synthesis, really what we're asking for would be what is the starting alcohol and what is the starting alkyl halide. Okay? You're responsible for acknowledging how to assume or put together those pieces. If we went through to look at the structure above, we're either forming this part or this part, depending on our perspective on red or blue. Because it was symmetric, it's hard to tell. These are both asymmetric, so what we want to do is to consider how we would break this apart. Okay? So we're addressing, should we break this bond or this bond? A or B? Which one should we be going through and synthesizing? Okay, well, how could we go through and do it? My recommendation, guess, try it. Okay, pick one. Let's say we picked the A path. Okay, if I pick that A path, we're talking about these electrons most likely associating with the oxygen, not the carbon. Why? Oxygen being more electronegative makes a lot of sense. So really what we're doing is thinking backwards, and what we can use is a retrosynthesis arrow. And we'd be saying we'd be going to a positive and a negative. For those people that really know retrosynthesis, you might be screaming because this isn't officially a retrosynthesis, because what I'm showing is unstable intermediates. Right? So this is a pseudo retrosynthesis at this point. What I'm trying to do is address the pieces first and then think about where they would come from. Right? So we'll color over the top when we have valid retrosynthesis starting pieces. Right? We'll pick first that negative oxygen, because that's a nice, easy negative oxygen. How would I get the negative oxygen? Right? Well, I got it by starting with the alcohol. Right? That was the whole point of the alcohol. So cool, there's that piece. That would be a valid retrosynthesis piece, because I'm starting with a reagent I'm allowed to have. So the idea on retrosynthesis is that we're pulling and breaking apart with intermediate structures, or intermediate's not the best word for it, intermediate structures kind of that exist. So can I go buy it? Trying to buy methoxide is a little bit harder. Methanol, significantly easier. Okay? How could I go through and make that carbocation? Well, the carbocation is not a stable structure, so I would need to revert it back to something that's stable. And if I again remember the pieces of my retrosynthesis and where I'm trying to end with for our Williamson ether, I could go through and put on the chloride or a bromide. Let's do bromide because that's what our example shows above. Okay, is that a stable structure? Yeah. Okay. So now what I've done is a retrosynthesis. Okay, officially what I should have done, retrosynthesis to alcohol and the alkyl halide. That would be a valid attempt at an answer. Okay, and that attempt is very careful wording. What we now have to do is think about, would this reaction work the way we want it to? So the next step in synthesis is actually test this. So if I were to test this, the first thing I'm going to do is my KOH, which is going to give me that strong negative. Okay? I would then react it with my alkyl halide. Strong negative to attack. Go, oh, well, it does the substitution. It should do exactly what it wants. This reaction, if I was going to try and set this up, and we'll maintain the kind of geometries of this, would be an SN2 mechanism. In the SN2 situation, we want a primary halide. We have a tertiary halide. Well, tertiary halides are not very prone to SN2 reactions. What does that mean? Well, is there a competing mechanism that could run with it? Yes, there is a competing mechanism. It would be an E2. Well, dang, if I have an E2 competing, this is likely going to shuttle out to not the ether I wanted, but to the alkene. Okay, so what does that mean? Well, that means this synthesis doesn't look like a good option. Okay, so what does that mean overall? Well, that means scrap it and we try again. But this time, instead of breaking what I had labeled as A, we'll break B. And now we want to go through and see what would happen. Okay, and we'll color code differently. So again, we can use our retrosynthesis as a thought process. We're talking about those electrons, again, going with the oxygen. Oxygen is more likely to carry those electrons. If we split that, we'd get our negative oxygen, and then we'd also just get a lonely methyl carbocation. That negative oxygen, not where I wanted to end. I wanted to end, or start rather, with an alcohol, so that would be a good retrosynthesis alcohol. The alkyl halide, the methyl isn't so great. I'd want to turn that into the alkyl halide, and so we've got a potential. If we overarch this a little bit better, what we'd be saying is we start with the alcohol and then BrCH3, and that would be my retrosynthesis answer. Okay? So what I've got drawn in blue is kind of my work or my thought process, but black is now valid. So again, we should go through and test it. We would run our KOH. Our KOH would go through and give us that negative. Cool. And now we'd want it to go through and attack our CH3Br. To break that open again in an SN2. We draw out our result and we would have our MTBE. As an SN2, we would want a sterically unhindered substrate. Good. So our substrate matches the way we want to. The nucleophile, however, is sterically hindered, which means it could act as a base. There's nothing acidic to remove, though. Because there's nothing acidic to remove, that base chemistry with an elimination isn't viable, and we really only get the SN2. So if we were to try to make MTBE, it makes sense to start with our tert-butyl ether or tert-butyl alcohol and react that with the methyl halide. That's going to be the better synthesis. Okay, so this is a challenging concept when we think about synthesis. Synthesis is not just one answer. Synthesis will likely result in 3 or 4 different answers. You have to decide which one is best. In the case of an exam where you're asked to show work, you write out whatever one you've got and hope for the best. If you have more time, you double back and you evaluate what made it good or bad. Maybe you lucked into it being good and you're fantastic and you don't have to worry about it. Maybe you lucked in or didn't luck into it and it's bad and you don't have time to fix it. You have at least proven that you understand the synthesis ideas. You just didn't have time. Okay? So take advantage of your strengths, show what you've got first, then move on. Okay? I'm not going to walk through the anisole, but we want to go through the same kind of idea. We want to break either the red or the blue and try and decide which one of those is going to result in the better synthesis. Okay? If you got questions about that one, I would highly encourage you to go through and ask me about that, because I would bet there's going to be an exam question on that. Okay? And yeah. Okay? So, could we get an internal ether? Yes. Internal ethers are known as a class as oxetanes, OXETANE, or oxetane. So depending on how many different atoms are in your cyclic structure, you could get a varying numbers of atoms. The epoxide becomes the most relevant one, which is where we have three things. We've already seen how to do this, and that we used MCPBA, lowercase m, capital C, PBA. Right? MCPBA had a fun little mechanism where it all happened at once in this one glorious little mechanism result, and we got our product. Okay? Williamson ether can make internal ethers or cyclic ethers just as easily as linear ethers. Okay? We still need an alkoxide and we still need the halide. Where this typically starts is a longer kind of synthesis process, and we would go all the way back to an alkene. And the fun part with the alkene is that our alkene, when we react it with halogens, we would form, first and foremost, that intermediate, that bromonium structure. Okay? That bromonium structure was highly unstable, kind of like an epoxide, and the remaining bromide could come in and attack. Well, one of the other things that we discussed is that it doesn't have to be bromide. It could just as easily be another nucleophile that's present, like water. Okay? So water could be used as the nucleophile to come in, attack, and break that open. And we would end up with, I'm a little nervous, oh wow, let's just pretend that not all of that showed up. We would end with what is known as the halohydrogen. Halo for our halogen, and then hydrogen because we've added OH. Okay, so we've added those pieces. That structure gives us the halogen part of our halide. It doesn't quite give us our alkoxide. So what do we need to do? Well, first we would need to add a strong base. And if we add that strong base, we could then deprotonate that. And we would get our negative oxygen. Now we have the alkoxide. That is our active reagent. So as soon as we add the KOH, we form the alkoxide. The alkyl halide's already present and can immediately react. And we would go through to form our epoxide, which is what we're showing here. Okay? Because I've shown some stereochemistry, let's address the stereochemistry on this epoxide. Where should those be? Because those are stereocenters. Should those be wedges and dashes, wedges? What's the deal? Right? Well, we have the dashed OH doing a backside attack. Since that bond didn't change, it should stay dashed. Because it's doing that attack, it's going to have to attack, because it's an SN2, from the backside of that bromine, which means that bond is also dashed. You should also be able to play around with the structure and realize there is no way you're going to be able to get that mixed, wedged, and dashed. Before we just say we got one product, we don't. We actually have multiple products. And where that's coming from is all the way back at that beginning. That pi bond reacted with p orbitals. Those electrons were either above, in the case of the structure shown, or those electrons could have reacted underneath, which means when we get to our epoxide at the end, we actually get two products. We could have got the system where they were both wedged or both dashed. So anytime you're doing an addition, you have the potential for two products. Make sure you consider that. Epoxides are extra particular about it. You will always get two products, at least two products, when looking at the epoxide synthesis, be it MCPBA or following the Williamson ether type synthesis. There was another thought that I had in the back of my, I remember what it was. Let's just say you were able to do a synthesis. So don't stress about where this structure came from, okay? But let's consider our Williamson ether. And in this case, you were somehow able to make this guy, okay? Purple box. Does the addition of the strong base result in the formation of the epoxide? No. Okay? And the reason being, again, comes down to our mechanism. This had to be a backside attack. If we put the bromine dashed, this oxygen is going to try and shuttle electrons where there's already electrons from the bromine, which is only going to push those electrons right back, and we don't get the epoxide forming. We have to have, everybody's favorite word, an anti-alignment of our leaving group and the nucleophile. Right? They have to be aimed opposite directions. It's particularly anti in the case of the, what are we looking at? Epoxides, because of that cyclic structure. In non-cyclic structures, you're still getting a backside attack, but we typically don't reference it as anti because they aren't connected yet. So they aren't really in anti-alignment. Okay? So that's just something to be aware of when we're looking at our epoxides. Next thing to look at is, remember, these came from alkenes, and the alkenes are looking at electrons both above and below the plane of the molecule, okay, because those are reacting with p orbitals. The p orbitals are either high electron density above or electron density underneath, which means you get two potential results. That means if you only wanted one, your yield is always going to be 50%, and that isn't great, okay? And that's a maximum. This is where a lot of organic chemistry synthesis is now kind of driven, is how do we create new reagents or catalysts that are going to limit some of those side reactions. And so another named reaction, Sharpless, was able to create a reagent, so a mixture of extra pieces that you would add to an epoxide reaction. And what that would do is force one of those products to form. Okay, and a lot of that depended on what you were adding. And so that adding part is the plus minus stuff that we're addressing down here, plus and minus DET. So those particular species are acting as a chiral catalyst to force one product over the other. Okay, so the addition of that chiral species changes how the reaction works. And if you've ever thought, well, that's nonsense, how could a single addition of that make a big deal? Try cutting with a knife that's been designed for a right-handed person. Right? You add a chirality to the knife, and it changes how you can use it. Right? The knife is kind of a weird example because you have to pay a lot of money to get knives built like that, but they're out there. You could do the same thing with scissors. Try cutting a piece of paper with scissors that have chirality to them, as opposed to using just a knife to cut the paper. So just a little bit of chirality in the reaction can cause massive changes in the end results. Right? None of that should have been really new. The new part is going to come into why epoxides. So epoxides are really synthetically useful because they still maintain the chemistry at two positions. Alkenes were useful because we had chemistry at both the carbons of an alkene. Epoxides still keep that chemistry and now tweak it a little bit that we can maximize a ring opening along with it. So epoxides do show up in nature a lot. We've got a bunch of examples up there. All of those are natural precursors to biomolecules that you may or may not be familiar with. It looks like 2 looks like some form of steroid in the process of being made. Same with 6. And we're seeing some kind of trans or some fatty acids, it looks like, it's coming together as well. So a lot of what dictates how epoxides ring open has to do with their conditions or the reagent conditions. Okay? And why that matters is going to come down to looking at those species. Okay? So if I looked at basic conditions, basic or neutral conditions, I'm looking at a negatively charged nucleophile. Right? And actually, let's rewind just a little bit. What do I need to force the ring to open? Okay, the easiest one for me personally to look at is the left one, so we're going to start with that. I need that ring to open. There are 3 potential bonds that could break. Of those 3, which is the easiest to break? It's a bit of a trick question, and really I should have asked, which is the hardest to break? The purple one's the hardest to break. right? Because it's a carbon-to-carbon bond. The blue and the red ones, because they're carbon to oxygen, are relatively easy to break open, right? Because of that polarity, because of the oxygen. So now the question is, how would we break those open? Well, think again of the polarity of that oxygen. That oxygen is withdrawing electrons, which means the carbons where the oxygens are connected are actually slightly positive, which means to cause the ring to break open, the species I have to add has to be a nucleophile, right? Why does that cause problems with our acidic conditions? Well, if we were under acidic conditions, the primary thing we add would be an acid. And if we add an acid, we're adding H+. What did we just say? To cause the epoxide to break open, I need a nucleophile. Okay, so the acidic conditions is a little bit different and a little bit more complicated. So we'll look at that one in a little bit. First, we'll address the basic conditions because it directly gives us the thing that we want. So the nucleophile now needs to be stabilized. So it needs to react with a positive thing. Well, as we just addressed, there were two positive things. We have the red and the blue carbons. Well, which one should the nucleophile be attached or directed towards? A lot of that's going to drive with the mechanism. Right? So if we consider this, the epoxide is stable enough on its own that it is not going to pop open on its own. Okay? It won't break open on its own. It has to be forced off. Okay? If it's being forced off, then we're looking more at a mechanism like the SN2 than the SN1. And in the SN2, if we remember, we were looking at a backside attack. Okay? And in that SN2 dynamic, we are primarily concerned about sterics. Okay? What does that mean? Well, if I go through and look at the red and the blue positions, they do differ. They differ by is that R group. That R group introduces a bit of sterics, which makes that blue path difficult to run, which means the red one is more likely to occur, so that when I run the reaction, I will end with my negative oxygen up there. There's my R group, there's my hydrogen, there's the negative oxygen, and then my nucleophile would be connected out here. Okay, so cool. We've now broken that epoxide open, and we've got the nucleophile connected. The nucleophile attacked the least substituted position because of that steric consideration. And a lot of that had to do with the bad leaving group. Right? We needed a strong nucleophile to force that negative charge to form. That is an unstable structure, so we would then follow this up as a step 2 with an acid, right? H3O+, H2O, something to acidify that, and what will end up happening is we'll end with our nucleophile, the stereochemistry is maintained at our chiral atom, and we will now, end with an alcohol. So there are basic or neutral conditions. Follow the chemistry that's associated with it as we move through this. Okay. After that, I think I've got some perhaps crisper drawings that I cheated on because I just threw the hydrogen on there. That's a second step in this. Okay, and so we have to be, I want you to be extra clear in here. Step 1, nucleophile. Step 2, H+ or acid workup. Okay, that's what's putting that hydrogen on there. Okay, so it was a poorly drawn reaction. So what happens if we now shift to acidic conditions? Because the acidic conditions become a little bit more challenging. Okay, you can already start to see some of the pieces that are coming together in this. So let's address these conditions. My face looks stupid, and usually does, but let's see if I can clean that up a little bit better. Okay, I feel a little bit happier about that. So if we look at acidic conditions, the primary thing present is the acid. We need to neutralize the acid first. We will do that by using the lone pairs from our oxygen. What does that do? Okay, well, not a whole lot to the epoxide. We didn't ring open, and actually I'm going to color code a little bit better. We didn't ring open, we kept the ring, but all we've done is now added a hydrogen, right? And that means our oxygen is now positively charged. The nucleophile, you'll note, in our kind of second reaction step, not a second, a second mechanistic step, not a second reaction step, you'll note is a little bit different than how we drew it before. On the previous slide, our nucleophile did have a lone pair, but I also showed a negative charge. That negative charge would only be allowed under basic conditions. I should not see that under acidic conditions, because if I'm under acidic, the nucleophile reacts with the hydrogen and we neutralize it. Okay? So the nucleophile has to have just electrons, no charge. Now we come back to the same question. The nucleophile either attacks that carbon or that carbon. The epoxide, and this is where things get a little bit kind of gray, the epoxide now is a little bit different because we have a good leaving group. So it wants to leave. Okay? It can't leave on its own, though, and that's an important statement to make. Okay? We cannot ring open until the nucleophile attacks. And we'll see why that's important here in a second. But that good leaving group now changes things. Because I have a good leaving group, that oxygen is already pulling on one set of those electrons more than the other. Okay? It's pulling more on either the blue or the red. Well, which one do you think? A decent guess would be, well, it's got to be the opposite one, because that's what chemistry does. It does the opposite of what we've already learned. It's a bit of an overstatement, but yes. Okay? Why would the blue one be more preferred? Well, if the oxygen's withdrawing electrons, it's making our carbons more and more positive. Well, where would be a more stable carbocation? The blue one, because it's more substituted. So in this case, the nucleophile, because it is weaker, won't directly attack the most available. It attacks the most stable. Okay? Because we're now looking at a more stable attack, when we go through and break this open, the result is that we've now gained that lone pair back on our oxygen. Our nucleophile still has to come in from the back side. This is going to force our R and our H upwards. Okay? We're seeing an inversion in stereochemistry at that point now, or theoretically an inversion in stereochemistry. Okay? And we've got our final product. Okay? In this case, the nucleophile has attacked the more substituted side, not the less substituted side. So we're getting a significant difference in the end result. The nucleophile changes where it's attacking. So it becomes very, very important to address the conditions under which you're running your epoxide reaction. If you follow the chemistry, these things and questions come up that allow you to address appropriately. If you don't address the chemistry, you have to memorize the result. Okay? And that there really isn't any way around it. You either understand the chemistry or you memorize the result. Okay? And again, I don't like those drawings, and we'll see more that I don't like those drawings in a second. But here we have the epoxide synthesis all summarized out for us. Again, the drawings are all awful, so I'm going to go through and fix those drawings real quickly here as we're kind of talking through it. So you need to kind of remember the big kind of lessons behind this. Okay? Under basic conditions, it's 2 steps: strong nucleophile, followed by acid workup. Okay, so that's important. Under acidic conditions, it's a different leaving group, for lack of a better descriptor. We have that positive hydrogen connected. Now the nucleophile can come in and attack. So this is all happening in one step. Okay, just one step, because we're having our acid connected to our nucleophile in one fell swoop, and it all happens at once. Okay, one pot. The conclusions that come out of these, under the basic type, okay, our nucleophile attacks least substituted. Okay? In the one type or acidic conditions, the nucleophile attacks the most substituted. Okay? So those are big differences between these. Okay? The next part that's kind of similar between both, totally lost where I was going. Anti-alignment. So the anti-alignment of our OH and our nucleophile, that is consistent between both of these. Okay? You might hear this referenced as an anti-addition. I feel that's a little bit weird to call it that, but I can understand why people would use it that way. I think what would be a better reference is, instead of calling it an anti-addition, acknowledge that the OH and the nucleophile need to be added on opposite sides of the old or former pi bond. Okay, so there's kind of our conclusions from our epoxides. This was a longer one. I do kind of apologize for that. And with that, we are done. Thanks for listening. That's not a stop button. Let's try that again. Where's my stop? There we go. Now we're done. Still not done.